Okay, so first of all, let's talk about localized air pollution. Okay, this is the type of air pollution that's produced by nature, and it's sometimes we help, sometimes we add a little bit to it, but for the most part, this is the type of pollution that just happens naturally. There's really not a whole lot we can do about it. It's not necessarily bad. It's not a negative type of pollution. Okay, it happens. There's really no pluses or minuses to it. It's just part of the problem, part of the system. If we, for the most part, these types of pollutants are spread out over the entire planet, and it's not a huge deal whatsoever. Okay. However, they become an issue when it starts to happen a whole bunch in one small area. That's when these type of pollutants become really, 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 really bad. So this would be like in cities like Los Angeles or New York City, really, really big cities with a very high population over a relatively small amount of area. Okay, so one type is something called a temperature inversion, and honestly, this is probably the main thing that we're going to talk about when we're talking about localized type of pollutants. This is usually what's causing it. So what in the world is a temperature inversion? Okay, first of all, as you go up in elevation, usually the temperature gets colder and colder and colder and colder. And we know something about heat, don't we? Heat tends to rise. Well, usually when the heat rises, so do the pollutants. Well, occasionally things can happen. Occasionally things can happen where warm air, it's like there's warm air and then there's a cold air and then there's warm air on top of it. So it's kind of like the cold air gets pocketed between two warm air, can't think of what I want to say.
Is that what creates
pockets of
smog
air?
cloud?
Yes, that's what creates smog. Basically, we have warm air where the city is, it's producing the pollution, and then we have the cold air, and then for some reason there is warm air up on top of it. And a lot of times,
What's smog?
really bad pollution caused by man.
Oh,
No,
I thought you were
fog.
talking about fog.
Well, the reason it's called smog is because it's foggy, but it's not fog by
Gotcha.
like water vapor. It's fog from pollution.
This was smart.
In your book, it tells you what smog stands for. Anyhow,
I didn't read that far.
okay. So one thing that causes this is, let's think about our West Coast. Let's think about LA. LA is known for having a pollution problem, correct? They have a really, really, really bad problem. That's why when you go to Los Angeles, you have to have a special kind of car. There's a lot of times there is days where you're not supposed to go outside because the pollution is so bad and it can be harmful. Well, the reason that LA, besides the fact that it's a huge city, is because a lot of times it gets caught in this thing called a temperature inversion. Well, basically what happens is LA is sandwiched between the ocean and mountain ranges. Okay, well, as you go up, it's supposed to get colder and colder and colder. And it doesn't always happen, but basically LA's in a valley. So as the warm ocean air kind of comes over, sometimes it could be warmer or cooler than the air in the valley. And so this cool air just kind of sits over this valley on the way to the mountain. And so therefore the heat is no longer rising, the pollutants are no longer rising, and they just kind of get stuck there. And as people get in their cars and businesses continue to produce their pollutants and continue to go throughout their day, the pollutants just start to increase and increase. And as long as that cold air is on top of the warm air, the pollutants can never go anywhere. So basically the only way we can get the pollutants to release is if somehow like a storm system comes in sometimes, or the wind starts to shift or something to get that cold air that's sitting on top of that warm air pocket to kind of warm up, so on and so forth. Eventually, sometimes for the most part, they only last a few days. Sometimes they can last longer, but eventually your weather's going to shift, and it usually solves its own problem. But that's why LA has days where there's a warning and they're supposed to stay inside. Okay, when we're talking about pollutants, there's actually like two types of pollutants. There's something called a primary pollutant, and there's something called a secondary pollutant. So we're going to talk about the primary pollutants first. These are produced directly by human activities. Okay, we do something to directly cause them. The 5 that we're going to talk about are particulates, sulfur compounds, organic compounds, carbon monoxide, and nitrogen oxides. So we're going to talk about these 5. We'll talk about each one individually. So first of all, let's talk about particulates. Okay, these are small particles of carbon or metals or tars or resins or asbestos. I mean, the list can go on and on. And yes, I see there's a typo. I'll fix that later. Okay, yes, I see that the list could be forever long. Everybody should probably recognize asbestos, right? That was used a long time ago in buildings before we knew of its danger. What happens if you breathe that? It gets into your lungs and it causes lung cancer, right? Okay, well, particulates is the same way. Particulates are little tiny things in the air that you can't exactly see, but when you breathe them in. Okay. Is anybody in a house doing demolition be like, oh, I'm breathing in asbestos, I'm going to stay in this house? No, because they're so tiny you can't really see them. And so particulates are dangerous because first of all, you usually don't even know that it's happening. Okay, so these are produced by grinding, spraying, like sometimes when people are cleaning, okay, if you're cleaning a construction site, a lot of times you're going to blow all of this sawdust or whatever up off the ground, and then if you're not careful, you'll start to inhale it. Another way is combustion, which is what cars do. So cars produce a lot of these particulates. 89% of these that occur are natural. So volcanoes produce a lot of particulates. When they erupt, they release all of this ash into the air, which honestly, which I'm sure we'll talk about in just a second, but all this ash in the air can actually, depending on how big the volcanic eruption is, it can affect the climate of the whole Earth for a period of a few years, depending on how much is released. Forest fires, again, fire is technically a type of combustion, which we talked about it in chemical reactions, and this can again produce ash because most combustion is not complete. You usually have something left over. Only 11% of the particulates are man-made. However, they're the ones that are the most harmful because we're usually surrounded by them the most. So some of these would be fly ash, which fly ash is actually what is created when it comes out of a coal-fired power plant. Whatever, you guys have seen the big smokestacks and all the smoke coming out of a power plant, right? Well, that's not just smoke. There's lots of stuff in it, and it's actually something called fly ash. So,
Are we going to talk about these volcanoes?
yes, I get to them eventually. Yes, the next slide. Okay, so are particulates bad? That doesn't sound, if 89% of them are naturally occurring, why are they so bad? Well, first of all, they can do something called seeding. Seeding gives water a surface to collect on. Water, especially in like clouds, it needs a surface to collect on to cause rain. So if we have a lot of particulates in the air, it actually increases rainfall. If the particulates are bad, it's increasing acid rainfall, which could lead to other problems down the line. There's actually something called seeding the clouds that sometimes we do when we're in a drought, when we need rain really, really bad. Sometimes they'll send airplanes, one of those really tiny airplanes, up into the clouds, and they'll release, I can't remember what, the silver iodide into the clouds, and it will give the water something to form on, and then it will make it rain. And so sometimes that's an option. Another thing that makes particulates bad is something called reflection. They can actually reflect sunlight back into the atmosphere or back into space. And what happens if sunlight isn't allowed to reach the surface, it's actually going to decrease our surface temperatures, which decreases the amount of plants we can grow, which decreases the effect of the greenhouse effect, which we just discussed. The greenhouse effect is a necessary evil, right? We need the greenhouse effect, but it's a fine line between too much and just enough, right? So it's kind of a fine line. When it comes to particulates, we have to consider how much we have and how much of the globe is it covering. Well, this brings us into volcanoes. So there's actually 3 volcanoes that I want to talk about that he spends a lot of time talking about in your book. The first one occurred in 1815, and it occurred in Indonesia. And when this volcano erupted, it made a 19 cubic miles of ash into the atmosphere. So think about how many 19 cubic miles. I mean, that's so big I have a hard time even fathoming what a cubic mile is in my mind. But 19 of them is just too large for me to even fathom. And honestly, what happens, well, with most volcanoes, especially in Indonesia and that part, they create tsunamis. Okay, so then that created tsunamis. And it resulted in a cooler summer, not just that year, but for a few years. Because as the ash goes into the surface and wind patterns travel it around the globe, it affects not just that area, but the entire globe. And so until all of that ash settles back down to the ground, it's going to be reflecting sunlight. This happened again in 1883, again in Indonesia. This time it was only 10 cubic miles of ash into the atmosphere. And it again produced tsunamis and a cooler summer. But the bad thing about 1850 and 1883 is we didn't really have great data collection abilities then. This happened again in 1992 in the Philippines. And this one only produced 2 cubic miles of ash, but we have physical data showing that it produced cooler summers. So if that one produced cooler summers with only 2 cubic feet or 2 cubic miles, I can't even imagine how many 19 cubic miles would have done. All right, so why are these particulates so bad as opposed to, okay, yes, they can block the sunlight. Yes, they can cause increased rainfall. But what else have they affect? Well, you guys have all heard the dinosaurs are extinct, right? We all know that. And there's lots and lots of theories as to why the dinosaurs, what led to the dinosaur extinction. Well, part of it is we can study the particulates. Okay, a lot of people think that the reason the dinosaurs went extinct is the meteor hit the earth, caused a whole bunch of ash to be thrown up into the air, which blocked the sunlight from reaching the air, which affected the amount of food, which killed off all the dinosaurs. Short story, correct? Well, what they actually did is in 1980, somebody was studying the Cretaceous and the Tertiary boundary, which is basically when the dinosaurs went extinct. We can dig down in Earth and we can study different layers, just like you can count the rings on a tree. Well, in 1980 they were studying this, and they noticed that when the rocks clay found between these periods is analyzed, it is found to have a high level of iridium, which is actually a very rare element. So that's kind of unusual for it to be a very, very big amount in this boundary, but this element is very, very common in meteorites and asteroids, and so that's what led to this idea of an asteroid hit the Earth. How do we know that? Because of the level of iridium found in that dust. And if you go below that layer, there's not very much found. If you go above that layer, there's not very much found. But for whatever reason, right between those boundaries, there is a high amount of ash and there's a high amount of iridium, which is what leads them to the meteorite theory. Okay. 10 years later, so in 1990, little side note, in the Yucatan Peninsula, which is in Mexico, they found a 120-mile wide impact crater from what was thought to be a 10-mile wide asteroid. And so in 1980, they kind of made this idea, this is what I think happened, and in 1990, they actually found a crater from the same period of time, and so now it kind of just solidifies that theory even more. Do we know if it's true or not? No, because no one was around back then, but we can only guess on what evidence we have. Okay, so how does this affect us? Basically, small particles of anything that you inhale is bad. Okay, now there are different degrees of bad, but basically when you inhale them, they get lodged in your lungs. Okay, that's what the lungs are supposed to do. They're supposed to kind of catch things, but too much can be bad. Smoking, exposure to asbestos, working in the coal dust. Coal miners usually have a lot of lung problems, right? These can all lead to lung cancers and breathing problems. Particulates are actually thought to contribute to 60,000 premature deaths. Okay, which the big one, anyone want to take a guess at what the big, out of smoking, exposure to asbestos, and working in coal dust, what the big one is? Probably, which one do people do to themselves? Smoking. Okay, the second type of particulate we're going to talk about is sulfur compounds. 2/3 of the sulfur compounds are naturally occurring, which means they happen naturally. One of them is H2S, and this is produced when volcanoes erupt and sometimes by anaerobic decay. Anaerobic decay is what happens, it's what the decay processes that happen when oxygen is not present. Okay, so it's kind of like the backwards of decay. A third of these sulfur compounds are man-made, and these are called sulfur oxides, and they exist in two forms. They exist as SO2 and SO3. H2S is not too bad. Okay, doesn't really affect a lot of processes, but these SOs, sulfur oxides, these can lead to a lot of side reactions, which are bad. 70 to 80% of these come from burning of coal, which, why do we burn coal? Produce electricity, produce energy, right? Some of it also comes from metal refining. Some metals are not usually found all by themselves. When people go panning for gold, do they always find gold all by itself in a nice pretty nugget? No, usually it's found in rocks. Usually it's found around other types of things, and it's usually found bonded to something else. Well, that's not just gold, it's most metals. So a lot of metals are actually found bonded with sulfur. So in order to purify these minerals, they kind of like roast them. And in the process, oxygen's in the air, so when they kind of, roasting is the best word for it. They heat them up, but they're not burning them. They're heating them up, and in the process, it might break the sulfur and the metal bond, and then the sulfur will bond with the oxygen in the air. Okay? This is also the cheapest way to get rid of them, is just release in the air. SO2 and SO3 is a gas. It's hard to control gases. It's hard to catch gases. It's hard to make sure they stay where they're supposed to go. So honestly, the majority of the time, they are just released into the air, which is part of the reason they're such a big problem, is because it's hard to control them. These sulfur oxides are extremely hard on your lungs. If you inhale them, it can cause a lot of problems. One example that I want to talk about is something called the London fog. This occurred over a 3-day time frame in 1952. Basically, England was trapped in a temperature inversion. Again, like I said, when we're talking about all of these pollution problems, usually it involves a temperature inversion. And that, again, is when a warm pocket of air gets trapped underneath a cold pocket of air. So basically what happened is it was in a temperature inversion, and since it was winter, the coal power plants were running full steam, producing pollutants after pollutants after pollutants. Well, since they were in a temperature inversion, the pollutants weren't rising. They were just building up, and they were building up more and more and more. So it caused all the pollution to stay in the city. Well, in that 3-day time frame, the death rate was increased there was an increase of 3,500 to 4,000 deaths just in those 3 days, and the 3 days prior to that and the 3 days after that. So in that 3-day time frame in London, 4,000 extra people died just from all of the pollutants that they were inhaling. Okay, now that being said, that probably wouldn't affect you guys. You guys are young and healthy, and you can probably handle some lung pollution because your lungs are young and healthy, and they haven't been exposed to a lot of other pollution. If you're older, a lot of these were like the elderly people, which again is no one in this classroom. You guys are not old. It honestly just kind of was a nice little push over the edge. Their lungs were already so damaged that breathing in all of these pollutants just gave them a little extra push that they wouldn't have necessarily had otherwise. It just, their lungs couldn't handle it because they already had so much damage. But over time, if you are exposed to this much pollution on a daily basis, are your lungs going to be able to continue to survive it? No. Okay, another thing about sulfur oxides is they also contribute to the acid rain. They react with water in the air to produce sulfuric acid, which can then be transformed into sulfuric acid. And this honestly increases the pH of rain. Rain usually has a pH of about 5.6, which is already slightly on the acidic. Remember, 7 on the pH scale is neutral. So 5.6 is already acidic, and sulfur oxides can decrease the pH of rain all the way down to 3.2. That's a pretty significant change in pH there. And that's a lot of change in pH. So why is acid rain bad? Well, first of all, it accelerates the corrosion of metals, and it can damage buildings. It can damage statues. It can damage marble really, really, really bad. Okay, it can cause a lot of maintenance necessary. So that's why in cities there's usually a lot of rundown buildings, so on and so forth. Sulfur oxides also can yellow paper, they can crack leather, they can acidify lakes and rivers, which can equal fish kills. So acid rain in itself Doesn't sound so bad, but it just has a lot of side effects that can start to damage everything around you. In our part of the world, what kind of bedrock do we have? Anyone know? Limestone. Okay, does anybody know what limestone is? What's limestone? Anyone know what it's made out of? Calcium
Oh, I knew that.
carbonate. Limestone is calcium carbonate. That sounds like something else that sometimes you take when you have acid reflux in your stomach. Anyone? Tums. Not that they're the same thing by any means, but they're not, but they kind of do the same thing. When you take a Tums, it kind of neutralizes the acid in your stomach, right? And it makes your stomach feel better. It makes the acid reflux decrease. We have limestone in our bedrock, so with acid rain, it neutralizes the acid rain, so we don't see a lot of these effects in our streams and in our lakes. But in places like Sweden, Norway, New York, Canada, they have a different type of bedrock. And so they have something similar, more similar to granite. And granite is actually it doesn't react real well with anything. And so it doesn't neutralize the acid rain. So in these parts of the country or in other countries, they have fishless lakes. So they just have these big bodies of water with no fish because the water's too acidic for the fish to live in. Okay, the third particulate that we're going to talk about is organic, or not the third particulate. The third primary pollutant that we're going to talk about is organic compounds. These types of compounds are hard to study. They're hard to test because there's so many of them. So therefore, it's hard to test them to determine what kind of side effects they have because, again, there's so many of them. We are often exposed to these types of pollutants in our homes. This leads to indoor pollution caused by building materials, plastics, and then what do, especially in the wintertime? It's cold outside. We shut all of our doors. We shut all of our windows. We turn off our attic fans. We basically aren't venting out our house at all. So throughout the winter, what do you think happens to all of these indoor pollutants? It's similar to the temperature inversion. They just start to build up, and they start to build up, and they start to build up, which is why as soon as it gets nice outside, people want to open up their doors and air it out because, well, first of all, you're trying to just air out your house, but why is that? You're actually trying to clear out all the pollutants. So airing out your house occasionally is actually a very good practice to do. And not only that, but our energy efficiency, we're trying to improve that, right? If we make our homes more energy efficient, which means less of our heat can escape or less of our cold can escape, so on and so forth, we're actually making indoor pollution worse because if no heat or cold can escape, we also can't vent our houses very well. And so it's actually increasing the amount of indoor pollution, but at the same time it's decreasing in other areas, so it's kind of like a tie, half a half, depending on how you look at it. One thing that they do study is something called a hydrocarbon. These types of compounds contain only hydrogen and only carbons, and they are honestly really, really, really long chains. Some of them are CH4, we talked about methane a little bit, right? They can be several carbons, 1 carbon, 5 carbons, lots of different hydrogens. There's lots of different types of these, so we just group them all together and we call them hydrocarbons. They usually come from the use of fossil fuels. Nature honestly produces the majority of them. Some of them are carcinogenic. Does everybody know what that means? They can produce cancer, but by themselves, they're usually not that bad. It's what they lead to secondary pollutants. So hydrocarbons themselves, they're naturally occurring. They really don't cause that many problems, but it is the secondary pollutants. I'm trying to think of an example of a hydrocarbon. Nope. That's all I got. I can't think of an example today.
Are we done?
Nope. The fourth type of primary pollution is carbon monoxide. 90% of carbon monoxide comes from natural sources, and again, doesn't cause a lot of issues. It's the 10% that we make that is causing a whole bunch of issues. In cities, this percentage can rise to 90 to 95%. And honestly, the majority of the carbon monoxide we create comes from incomplete combustion. So honestly, we're talking about transportation. Now, does everybody remember what combustion is? Back when we did chemical reactions.
The equation.
Chemical reaction is fire, right? Something plus oxygen is burned and it produces carbon dioxide and water. That's what combustion is. Well, incomplete combustion is when we basically don't have enough oxygen. We're running out of oxygen. So like if a room is completely sealed off and you're burning a fire in it, is that fire going to burn forever? No, it's going to burn until it runs out of carbon. Well, what happens when it's not technically burning anymore? Is it still kind of smoking a little bit? Yes. Okay, well, this is part of incomplete combustion. Okay, incomplete combustion is when basically there's not enough oxygen. So instead of producing solely carbon dioxide and water, it'll start to produce carbon monoxide, which we see down here in this, which we see down here in this, down here. And then sometimes if we run out of even more oxygen, it'll just produce carbon, which is just kind of like all the ash that's left over in a fireplace. Hydrogen is kind of bossy when it comes to oxygen. That's how I like to say it. So if we're running out of oxygen, hydrogen's going to steal it all, and we're going to make water. It's always going to make water because hydrogen is bossy and he's going to steal all the oxygens. So what ends up happening is carbon's the one that's left without any oxygen. And so that's why we'll form water in every single one of these reactions, but we'll start to form carbon monoxide versus carbon. Okay, so why is CO so dangerous? Why is carbon monoxide? Carbon dioxide is around us all the time. We produce carbon dioxide. Well, the reason carbon monoxide is so dangerous is because it actually replaces the carbon dioxide in your blood. So this is, honestly, this is how your blood works. Your hemoglobin in your blood, it picks up oxygen in your lungs, it takes it to your cells, it drops it off, it picks up the carbon dioxide, brings it back to your lungs, you breathe out the carbon dioxide, it sits there and it waits for you to breathe back in oxygen, it takes the oxygens to your cells, and it just kind of goes in this giant cycle back and forth. I'm going to take oxygen, I'm going to carry back carbon dioxide. Just kind of goes back and forth, back and forth. This is a reversible reaction. We can reuse our hemoglobin over and over and over and over and over again. Well, carbon monoxide really likes hemoglobin, so once it bonds to it, it doesn't let go. So that's why people who have carbon monoxide poisoning will actually pass out because they're actually having a lack of oxygen to their brain. There's not enough hemoglobin to transport the oxygen to the brain, so therefore you start to pass out. Well, if nobody finds a person passed out, they'll eventually semi-suffocate because there's no more hemoglobin to carry oxygen to where it needs to go, and so basically it's like they're suffocating. Okay, now we're exposed to carbon monoxide all the time. A little bit of carbon monoxide is okay. It's not going to kill you. It's when the carbon monoxide that you're inhaling is faster than the amount of hemoglobin you can produce. So it's when you breathe in more carbon monoxide than hemoglobin you're making, that's when it's bad. Because then we can't produce hemoglobin fast enough to bond with the oxygen. And so that's when you'll start to pass out. That's when you'll start to have issues. At first, it affects your ability to see and think, which is why you pass out. This is also why some people start to get a little crazy if they've been cooped up for a while. Sometimes it's because they've been inhaling too much carbon monoxide. But as the levels get worse and worse and worse, it can actually lead to death, especially if it goes unnoticed. All right, the fifth primary pollutant is something called nitrogen oxides. N2O is 100% natural. Bacteria create this. It's not too bad. Okay, it's NO that's bad. Okay. This is 80% of it. This occurs oftentimes in lightning, volcano. Also, it can form in a type of decay. 20% of it, however, is man-made, and it is man-made through combustion. Another nitrogen oxide that can be bad is NO2. NO2 is really bad because it is 100% man-made. This is not naturally made in natural reactants. NO2 is man-made because it only occurs when we have high temperature combustions. So a lot of times in our cars, we are trying to combust our gas as well as possible. That's what increases our gas mileage. Well, in the process, it increases the pressure. When we increase the pressure of the gas, it increases the temperature. So we're burning our fuel at a very, very high temperature. And I don't know about you guys, but there's not a whole lot of places for oxygen to get into your engine, right? It's a pretty closed off system. So what ends up happening as the temperature increases and we run out of oxygen, we start to produce more and more NO2s. Okay? I'm just going to start calling these nitrogen oxides because I'm talking about NO and NO2. These are very hard on your lungs. They can contribute to acid rains, and they can also contribute to the secondary pollutants that we're going to talk about in just a second. NOs, nitrogen oxides, are very hard to control because if you remember back to the last chapter when we talked about the percentage of nitrogen, nitrogen is 71% of our atmosphere. So it's really hard to produce or hard to control the amount of nitrogen oxides produced because there's so much nitrogen in the air for oxygen to bond with. So all we need is some high temperatures, and the reactants are already there. It just needs a little push. So these are really hard to control. So let's start talking about our secondary pollutants. Primary pollutants are, for the most part, man-made. Once they're in the atmosphere, however, they can undergo other reactions to make possibly worse pollutants. So when I've been talking about the primary pollutants so far, and I've said several times, they're not so bad. It's what they do once they're created that is bad. Oftentimes, these reactions are precipitated or increase when they're in the presence of light. Can we control the amount of light outside? No. And so therefore, we produce primary pollutants, which then go on to make possibly other worse pollutants, and this whole process is made faster by exposure to light. And so once we create the primary pollutants, this just kind of snowballs into the whole reaction. So one of these can be called photochemical smog. So if we look at this, let's look at our nitrogen oxides that we were just talking about. Here we have NO2, and in the presence of our atmosphere, we have oxygen, right? So we have NO bonding with oxygen, and it actually makes two NO2s, which was, if you remember what I just said, it is 100% man-made, correct? What happens then is the NO2 is exposed to visible light, and in the process, it breaks apart NO and O. What did I just talk about oxygen when I was re-explaining the ozone layer? He's a diatomic molecule. He will do anything in his power to bond to somebody else. It's all in who is he going to bond to. So now he is free to bond to somebody else. Oh, so now we have an SO2, which is also a primary pollutant, right? He bonds to SO2, creating SO3. Or he can come over here and he can bond with another O2 molecule in the air and form O3, which is ozone. Ozone is a bad secondary pollutant. But what? Ms. Hackett, we just talked about the ozone layer and how important it is, and we need more ozone. Okay? Ozone is really, really, really good up there in the stratosphere because it blocks our radiation from the sun. But down here on the surface of Earth, ozone is bad. Okay? It is very, very irritating to the eyes and the respiratory system. It'll cause you to cough really bad. It can cause some other lung issues if you're exposed to it for a really long time. It can also cause chromosome damage, which can lead to cancers, which could lead to reproductive issues. Okay? It can also inhibit photosynthesis, or in other words, stop it. Keep photosynthesis from happening, so in other words, plants can't grow the way they're supposed to. So ozone up there in the stratosphere, good. Ozone down here on Earth, the surface of Earth, bad. Okay. The reason ozone is bad is because it can form aldehydes, which can be carcinogenic, which again can cause cancer. The most famous aldehyde that you guys have all heard of is formaldehyde. Formaldehyde used to be used in a lot of things to preserve them, right? Well, it's actually ozone can form aldehydes, which one type is formaldehyde. If you breathe it in or ingest it, it can cause cancer. Okay. They can also produce something called a peroxy. I actually not even pretend like I can pronounce that, but it's just called a PAN. That's all I've ever been told. These are very, very toxic to your eyes and lungs. Again, they're very, very irritating. And these are also very hard to control because our NOs are hard to control. Why are our NOs hard to control? Our nitrogen oxides. because nitrogen is 71% of our atmosphere, right? If it's the majority of our atmosphere, it's really, really hard to control our nitrogen oxides. Okay? So let's look at kind of the breakdown. So we've been talking about these 5 main types. Okay? The particulates make up about 3% of our air pollutants. Our sulfur oxides make up about 10% of our air pollutants. Those organic compounds make up about 10% as well. The carbon monoxide makes up 63% of our pollutants. And then our nitrogen oxides are down there back again around 13%. So if you look at this, the majority of our air pollutants is carbon monoxide. Does anybody remember where I said the majority of carbon monoxide comes from? Cars, right? Transportation. Okay, transportation accounts for 40 to 60% of our total pollution, but it only accounts for 12 to 15% of the toxic in our pollution. Okay, the reason it produces a lot of pollution, but it doesn't produce the toxic pollution, is because it doesn't usually produce our sulfur oxides, which are our most toxic pollutants. Okay, metal refining and coal burning, these are our most toxic. They don't produce the highest percentage, but they produce the most toxic pollutants. So it's kind of, again, a teeter-totter. Transportation produces a lot of pollutants, but they're not so bad for you. Metal refining and coal burning don't produce as much pollutants, but they're a lot worse for you. So it's kind of, again, a teeter-totter, which is better. More pollutant, but not as toxic, or less pollutant, but more toxic. So it's just kind of a give-me. So let's talk about transportation a lot. Okay, transportation produces 3 main pollutants. The first 2 are hydrocarbons and carbon monoxide. Again, these are produced from the incomplete combustion. The reason that they are produced is because the fuel to oxygen ratio is too small. If our fuel to oxygen ratio is too small, we run out of oxygen. If we run out of oxygen, we can't do combustion. And so therefore we start to produce other byproducts besides carbon dioxide. Okay, the other pollutant that transportation can produce is our nitrogen oxides. And the reason it produces nitrogen oxides is because of the high temperatures. Again, when we try to increase our gas mileage, we're trying to combust our fuel as best as possible. So we increase the pressure in the pistons. Okay, when we increase the pressure, it increases the temperature. As we increase the temperature and we start to run out of oxygen, it produces these nitrogen oxides. Okay, so it's kind of, again, there's no perfect engine. It's like if we try to maximize our gas mileage, but we increase the temperature at the same time, well, yeah, we're producing less hydrocarbons and less carbon monoxide, but we're producing more nitrogen oxides. If we lower the temperatures to produce less nitrogen oxides, we're not going to do as good of complete combustion, and we're going to get more hydrocarbons and more carbon monoxide. So again, are you guys starting to see that when we're dealing with pollution, it's a balancing act? What is the lesser evil? But in cars, we can actually vary this ratio. And so it's kind of, we've actually found a balance. Okay, if we increase the ratio, we can, aka we have more oxygen to fuel, and I believe 14 to 1 is what I'm talking about. If we increase the ratio of gas to oxygen, we have more complete combustion, which means we have less hydrocarbons. We have less carbon monoxide coming out of our car engines. Okay? However, this causes a temperature rise, which increases our nitrogen oxides. If we lower the amount of oxygen, we're going to have less nitrogen oxides, but we're going to have more hydrocarbons and more carbon monoxide. If our ratio is above 16.1, all of the pollutants come down. So that's a really 16 to 1 gas to oxygen ratio is perfect because it is the point in which all of our pollutants start to come down. However, when we do that, the car doesn't run very well. It misfires. It can backfire. It drives real shaky. It's like it's going to die all the time. And so honestly, there's just this really, really fine line between how many pollutants do we need to create, how well is the car going to run, so on and so forth. Well, since the majority of us use transportation on a daily basis, we have tried to implement some regulations to try to limit the pollutants. Okay, the big advance was the catalytic converter. I believe this was in the 50s or 60s. Basically what happens is the catalytic converter uses platinum and polonium, and these are actually very expensive elements, which is why if you've ever tried to replace the converter, it's very expensive because these elements are very expensive. Basically what happens is this converter catalyzes the waste to make further combustion reactions, and basically all the leftover carbon monoxide and hydrogens from the engine are then they go through another reaction to try to make them react into something that is safe for the environment. However, back in the 1960s, when this was first created, we didn't have unleaded fuel, we had leaded fuel. Well, leaded fuel kills our converters. It damages the reactants and it actually makes them go bad really, really, really fast, so it ruins a converter. However, unleaded fuel wasn't really introduced a whole lot, and when it was introduced, it was more expensive. So people would put the cheaper gas in there, which was leaded, which would then ruin the catalytic converter. So therefore, the whole point of having the catalytic converter was gone because it no longer worked properly. So over time, we have made lots of adjustments to make it work more efficiently with less pollutants. We have also started to add rhodium into some of the converters. This converts our nitrogen oxides into nitrogen and oxygen, which are safe for the environment. That's what's in our atmosphere already. We actually have added oxygen sensors so that we know when our oxygen levels are getting too low in our engine so that we're doing incomplete combustion. We also have started adding different mixtures of our gas. We have our octane rating, correct? Different mixtures of gas produce different results. Okay, so the government actually sets expectations per car. Previous to 1968, you can see that the expectations were pretty high. Or not the expectations, what they allowed. They allowed 15 grams of hydrocarbon per mile. I mean, that's a lot when you think about how many miles people drive every single day. They would allow 90 grams of carbon monoxide per mile. They would allow 6.2 grams of our nitrogen oxides per mile. What is the big difference from the 1960s to now when we're talking about pollutants coming from cars? We have a lot more cars, don't we? I mean, in the 1960s, we maybe had one car per family, and now families have at least 2 cars, and then once the kids start getting into teenage land, sometimes 3 or 4 cars per family. Okay, everybody has a car. And so the levels have gone down, right? So our efficiency of our cars has increased, but the number of cars is increasing. So do you think the pollutants that we're releasing is decreasing? No. We're releasing the same amount of pollutants that we were in the 1960s. The only difference is we have 2, 3, 4, 10 times the number of cars. And so we're releasing the same amount of pollutants. So again, teeter-totter. We have more cars, so we have to keep changing these regulations because we don't want to produce more pollutants than we can technically handle. All right, so let's spend a little bit of time talking about diesels because we all know, or not we all know, but diesels have a little bit higher efficiency of gas consumption. They can usually get more miles per gallon. The reason that they can have a little bit better gas mileage is because they have a higher compression. When we compress the gas, it can technically combust a little bit better. More complete combustion leads to better gas mileage, which therefore lessens the amount of hydrocarbons and the amount of carbon monoxide released because we're doing complete combustion. However, what happens when we do better complete combustion? That usually increases what? The temperature, which increases our nitrogen oxides, right? And so yes, diesels are more fuel efficient, but they also produce more nitrogen oxides. But what is really bad, because they do produce a little bit more nitrogen oxides, but not too bad of a ratio. But why diesels why they are thought to be more pollutant is because they release a lot of particulates, which is why if you're behind a semi, which if you're behind a bus, if you're behind a giant truck, they have the gray smoke coming out as opposed to cars. For the most part, cars, you can't really see their exhaust, correct? Well, the reason why is because diesels are releasing all of these particulates. They are limited to 0.2 grams per mile, and we've actually started to add a little bit of mixtures into the exhaust, and this tries to convert the NOs back into N2 and water. So, again, they have better gas mileage, but they produce pollutants. So it's just, again, it's not a perfect world. We don't have a perfect answer to everything. We're just trying to figure it out. So basically, we need to come up with some alternative fuels. In order to improve the pollution, the big way is we need to lower our dependence on imported oil. There are several other ways that we can do the same effects without producing as much pollution. We have some of the alternative fuels that we're looking into are methanol, ethanol, compressed natural gas, propane, biodiesel, and of course electricity. Okay, so let's talk about each one of these for just a second. So first of all, let's talk about methanol. Methanol can actually also be called methyl alcohol because it has an alcohol group. If you look at the chemical formula of it, does everybody see the OH at the end? That's the alcohol group. That's why it's called methanol. Anytime you see all, we have an oxygen and hydroxide towards the end. Methyl alcohol is actually produced from natural gas or coal. It has a much higher octane value. It has more horsepower. It has a faster acceleration, and it's cheaper. That sounds pretty good, right? Win-win situation. However, it's only about half as efficient. So it doesn't burn quite as well. It doesn't work in our engines quite as well. So therefore, yes, it produces less pollutants, but you need twice as much to go the same distance. So it's kind of like, again, we need twice as much of it. So in the grand scheme of things, are we really producing less pollutants? Kind of depends on how you look at it. However, how methanol is good is it can be mixed with gas. So gas has good qualities. Methanol has good qualities. Both of them by themselves do not have great qualities, right? And so we actually can mix them sometimes. So if we talk about methanol 100, which is 100% pure methanol, not mixed with anything, it produces 90% less hydrocarbons, but it burns clear. So therefore, in like a car wreck, would we be able to, it would cause explosions would be a lot more common and problematic because we couldn't see them coming. Okay. Secondly, it's really, really hard to start your car in the cold, which the way we are around here these days, one day it's fine, the next day it's freezing, right? However, if we make it M85, which means it's a mixture of methanol and alcohol, or not, methanol and gas, we can start it in the cold. It burns with a yellow flame, so therefore in car collisions we could actually see it, we could prevent the explosion, so on and so forth. It produces 35% less hydrocarbons. So we're not getting as big of the benefit, but it's still improving it to some degree. So anything we can get, we'll take at this point in time. Another thing about methanol that is bad is it's water soluble. What does water soluble mean? It can dissolve in water, which means if it were to get released into the environment, we would have a really hard time separating it from our lakes and our streams. It would just be a pollutant that would be really hard to do anything about. Okay, the next one we're going to talk about is ethanol. Very similar to methanol. It's ethyl alcohol. Again, we see that OH group. That's why it's called an alcohol. This ethanol can be made from crops. Some of the crops that we use are sugarcane and corn. The one that we use a lot of the time around here is corn. This is currently added to gas to boost our octane values. It is more efficient than methanol, but it is also more expensive. And it is only 2/3 as good as gas. So gas is still better than ethanol. So ethanol might produce less pollutants, but again, we're going to need more of it to go the same amount of distance. So again, which is better, which is worse. Another thing that's kind of bad about ethanol is we have to use our food crop to produce it. If we took 100% of our corn, so the corn that is produced to feed us versus our livestock versus every bit of corn that we produce, if we used all of it, we would only get 18% of our fuel needs. So is this a viable option, really? No. Plus, we need the food to feed our livestock. The majority of the food that is given to livestock is primarily made out of corn. And so if we used it all for fuel consumption, what would we feed our livestock? So it's kind of like honestly, I feel like this is probably not a good option at all. The next one is compressed natural gas. The U.S. has a bigger supply of natural gas than oil. Okay, natural gas is often found around oil. Okay, but we have a much bigger supply of natural gas than oil, so therefore we wouldn't have to import it in. Honestly, what we would do is we would compress it into heavy walled tanks. Okay, well, I don't know about you guys, but what happens if you put a really heavy gas tank on a car? It's going to increase the mass of it. It's going to weigh it down on the road. What happens? The heavier your car is, what happens to gas mileage? Decreases. So yes, maybe we would be producing less pollutants, but we would need more gas because the car would weigh more. So it would make our car less efficient in other ways. It does produce 40 to 90% less hydrocarbons of gas. It produces 50 to 90% less carbon monoxide and 10 to 30% less carbon dioxide. But again, we would need more of it because it would make our cars less efficient. So again, it's just, honestly, it's just a big toss-up. What's the best? What's worse? Who knows? Another type of alternate fuel would be propane. This again, we use propane a lot in our houses to heat our houses, right? But propane in transportation is used a lot on buses. They again produce lower hydrocarbons and lower nitrogen oxides, but again, it's a gas, which requires a heavier tank, which makes less gas mileage, which makes more refueling, more expensive in the long run possibly. Most of propane comes from petroleum refining. So if we can get propane, the whole point in trying to find alternate fuels is to try to lower our dependence on imported oil. So if we get propane from oil refining, that's not really solving our problem, is it? Because we would probably have to import this in as well. Oh, we're almost done. The fifth alternative is biodiesel. And basically what we do here is we can take natural fats and oils and we can burn them, and in the process they can create a diesel. Some of the oils that I'm talking about is like canola oil or soy oil. These can replace the diesel fuel, or they can be mixed with diesel because just like I was explaining with the methanol itself wasn't a great thing, but if we mixed it with gas and made it better. Same thing here. If we took diesel and mixed it with our biodiesel, it would make it possibly produce 10% less energy, but it's biodegradable. It wouldn't pollute the environment. It would be renewable. So again, less efficient, but less pollutants at the same time. So I think this one's actually a pretty viable option. And then last but not least is electricity. Okay, electricity is a pretty good alternate energy. A lot of the cars in Europe are electric, right? But where does electricity come from? Coal burning power plants. So what happens in order to create electricity? We have to make pollutants. So do electric cars produce pollutants? No. But in order to produce the electricity for our electric cars, do we have to produce pollutants? Yes. So is it really solving the problem? No, it's producing pollutants in a byproduct, kind of, right? Now, if we could produce the electricity from maybe wind power or nuclear power, maybe. But right now in the United States, producing it from our coal power plants would really not solve the problem. All right, so let's talk about industry a little bit. Industry is the one that is producing a lot of our pollutants. And one of the main sources of the particulates in the air, again, the things that we're inhaling, is something called fly ash. Fly ash is what goes up the smokestacks in a coal burning power plant. It's what you see in the smoke that's coming out of the towers. They have several things that they do to try to reduce the fly ash. Well, the first one is called a mechanical collector. Basically, it creates a tornado, basically. It spins the wind really fast, which causes the particulates to be thrown to the outside of the stack. They're thrown to the outside, they kind of stick there, and then they aren't released with the rest of the gas that's being released outside. This works for really large particles, but the really small particles, they're still going to be released, so it doesn't really solve all of the problem. So then sometimes we use something called a wet collector. This is when our exhaust from our power plants is put through kind of like a rainstorm before it's released out. This one works really good for small particulates, but not really for the large ones. So it's kind of like maybe if we could do both of these at the same time, maybe we would get, but trying to do both of these at the same time would probably be really expensive. Some other ones that they try to do is something called a fabric filter. This is honestly like a giant vacuum cleaner. It's like it sucks the exhaust through this really thick fabric or woven or felt, really, really, really thick. And as the gas is being sucked through this really thick fabric, hopefully they're hoping that the particulates are going to stick to the fabric. Just like when you guys are in smog, sometimes they cover up their face so they're not breathing in everything in the air. Another one is something called an electrostatic precipitator. And this is actually the best method that can be used. Honestly, what happens is a very high voltage discharge ionizes the air, which that sounds really complicated. But basically, it is putting it's taking the molecules in the air and making them charged. What happens to charged things like magnets? If we have a whole bunch of magnets all together, they're going to start attracting each other, correct? So if we can make the items in our air charged, they're going to try to attract these particulates and in the process carry them with them as they're traveling to the opposite. So if it's a positive, it's going to be attracted to the negative plate. So hopefully it'll take the particulates with them. This actually removes 99% of particles. However, it's really, really expensive to install. And it uses a lot of electricity because in order to do this, we have to discharge a high voltage. And so we're saving pollutants, but we're using more, it requires more electricity. So again, it's just kind of a teeter-totter. Our sulfur oxides and our nitrogen oxides can be removed by scrubbers or absorbed by filters. I don't know why some of that is black, but basically our SO2, which we talked about, could be bad sometimes. Okay, could be changed into SO3, which can then be changed into sulfuric acid. Sulfuric acid bad makes acid rain. However, we can also sell sulfuric acid. People use sulfuric acid to make other products. So if we can trap it and make sulfuric acid, we can make money from our waste products, correct? Good, good. SO2 can also be burned with limestone or dolomite, which can create a solid. If we can somehow get our particulates or our pollution into a solid form, it's a lot easier to control it. The hard thing about sulfur oxides and nitrogen oxides is they're in gas form, so it's hard to control them. So if we make them into solids, we can dispose of them in other ways. Nitrogen oxides can also be reduced by lowering the temperatures of combustion. But again, what happens if we lower the temperatures of combustion? We are no longer doing complete combustion and we start producing hydrocarbons and carbon monoxide. So it reduces the amount of power. However, we can take our nitrogen oxides and we can scrub them with bleach to produce nitric acid. What do you think we could do with the nitric acid then? Sell it, because it's a product that we can make money off of. These are then water soluble. Nitric acid is also water soluble, so which means we can dump it down the sink. It's not going to harm the environment. So basically, we need to be making progress. Congress has enacted the Clean Air Act, and basically it has set requirements for cities and industries to meet. And you have noticed that over time, we are going down. And these percentages are how much decrease we've seen. So between 1970 to 1990, we saw a decrease of 61%. That's pretty good. Okay, as long as all of these numbers are continuing to be negative, good. As long as they don't start to rise, that's when it would be bad. So, homework, page 219, numbers 1 through 6. Do you guys like my little comics at the end?
That waste of time.
Not really.